So Coulomb said that there is a force between these two charges, and we also know that because these two charges are like charges. So these are known as field lines and these are vectors. So this has a particular direction and it has a magnitude. The electric field is represented by the letter E, which is a vector quantity opposite in polarity separated by a distance 2a. Then this is known as an electric dipole. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, Mysuru. And we were discussing about electric fields and charges. And we actually saw what charges were, how they were discovered, how they interacted with everything around them. Now we are going to learn more about charges, how they interact with the nature around them, how their behavior is, and how they affect everything around them. So we actually saw what Coulomb said about the force between two charged particles. But we did not say how he arrived at this equation or what this equation actually means. Force is a vector quantity. So vector quantities are slightly difficult to understand, but there is an easy way to understand this. So what did Coulomb exactly say about this law and what did he mean by this? So he said that if there are two charges, that is Q and another Q. Let's assume for the time being that both of these charges are positive and they are separated by a distance of r. So two charges are separated by a distance of r. So Coulomb said that there is a force between these two charges. And we also know that because these two charges are like charges or they have the same sign. So these two will be repelling each other. So there is a force between these two charges and that is a repelling force because they are like charges. They repel each other. That is, this will exert a force in this direction and this will be going in this direction because they are like charges. So what Coulomb said was the force will be proportional to the product of their charges, that is Q1 and Q2, and inversely proportional to the square of the distance between them. And to avoid the proportionality sign, he introduced a constant which is K. We'll get to that immediately, but wait. So there are two charges which is positive Q and positive Q. So it is denoted as Q1 and Q2 and they are r distance apart. So since this is a vector quantity, we have to denote it by vector terms. So we have to introduce a vector which is a unit vector, which just means that vector quantities does not just have magnitude, they also have direction. To indicate this direction, we have this unit vector. So what this means is that the force is from R1 to R2. That means that the force exerted is being in the direction from Q1 to Q2. From this direction, it is going to this direction. So these were the initial observations of Coulomb. They were exerting a force on each other and the force will be directly proportional to the product of their charges, inversely proportional to the square of the distance between them, and the direction will be denoted by a unit vector which is represented here. And now we also have to explain which force is experienced by which material or which particle. For example, vector quantities, we have to specify in which direction, which material, which particle is experiencing the force. For example, we are talking about two particles here or 2 point charges, that is Q1 and Q2. So we have to explain in which direction is the force acting, which is done by the unit vector. And now we have to explain what is the force acting on it using these two notations. So we can say that the force experienced by the charged particle Q2 due to Q1 is given by F12 equals K into Q1, Q2 divided by square of the distance between them, and the direction is given by the unit vector. So we know that this is the direction of the force. So we know the direction of the force F12 is in the direction of R, which is in this direction. But there is also another force which is experienced by Q1 due to Q2. And that force will be in the opposite direction indicated by F21. So if we take just these two directions, we can find out that F12 is in one direction while F21 is in the opposite direction. What does this actually mean? This means that these forces are equal in magnitude but opposite in direction. How do we know that? Because the equation for both of these forces is given by Q1, Q2 divided by R square, constant K, Q1, Q2 divided by R square, but the direction of the force which is acting changes, because for one it will be R12 and for the other force it will be R21, because the line of direction of force is different. One will be in this direction and the other one will be in the opposite direction. So only the direction changes in this case. But since the direction changes, these both forces are acting in opposite direction, which means that F12, vector F12 is equal to minus vector F21, which means that they are acting equal but opposite in direction. So this also proves one more thing, that the Coulomb's law is in agreement with Newton's third law of motion. Every action has equal and opposite reaction. So that is meant by this equation. So the main thing again is that Coulomb found out there is a force between two charged particles and he arrived at this inference, which he converted into an equation. And since this is a vector quantity, direction and magnitude both matters, and the force acting will be along this line. So if this is Q1 and Q2, the direction will be R12, which is represented by R12 caps, or you can simply call it unit vector R12, and we can denote it like this. So this will indicate the direction of the force acting. And finally, if Q2 is acting on Q1, everything will be same, just the signs will be interchanged. So F12 will be equal to minus F21 because it is in the opposite direction. So that is one assumption that Coulomb also agrees with. So what Coulomb basically said was that the force of attraction, if they are unlike charges, that is, if one is negative and one is positive, then this will be a negative sign will be introduced here. If both are positive, then the equation will be positive. If both are also negative, then also the equation will be positive. That is because if both are positive, then the direction will be in this direction. That is because if both of them are repelling forces, then the direction of force will be obviously in that direction or this direction, depending on the force, because both are positive charges and they are repelling by nature, and they'll just push one another and they'll just move away. So depending on the sign of the charges you have taken into account, the force between them will also change. It can be attractive, it can be repulsive, and the negative sign or the positive sign will just indicate that if the forces are attractive or repulsive. So as unit vector indicates the direction, the force vector also indicates which particle is experiencing the force due to which particle. Here in this example, it is force experienced by 2 because of 1. And like that, you have to understand what vectors actually entails. It gives a huge amount of details, so you should clearly write this. So we have actually studied about how we can calculate the force between two charged particles. But why do we need this? And how can we physically signify this force? And is this the line force? Is it all around it? Is it different for different charges? And how does it actually represent itself? So we can take a look at all that. So for that, we are going to introduce the concept of field, which we briefly explained in the last class, which actually means that it is the force experienced around that particle, or just the particle has influence around a large area or some area around it, and that area limit is known as the electric field of that particle. So for example, let's say you have a positive charge. Okay, and it will have an electric field around it. Even if it is positive or even if it is negative, it will have an electric field around it. The electric field is explained as the force a charged particle experienced when placed at a point. which simply means that there is an area around the charge where the force of that particle will be felt. And that area, within that area, if you place a positive charge, this will experience a force. And we have clearly explained that by Coulomb's law. And this will experience a force. This is actually termed as electric field. So to put it into simple perspectives, we can say that imagine that you are in a river. Okay, the river is flowing and you are in a river. And you will feel that if it's a free flowing river, you will feel a push. You will feel the force of the river pushing against you. Here, you are the unit positive charge and the river is the representation of the electric field. So again, imagine that there is a sprinkler. So this is a sprinkler which sprays water in all directions like this. So imagine that this is a crop. Let's say it's a flower or a potato or whatever. So here, water sprinkler can exert its water pressure onto this potato or flower or whatever plant, and it will experience a pull or like a push, right? And let's say there is a flower outside this. Let's say there is a flower outside the limit or the area which the sprinkler has effective force on. And then outside this area, this flower is unaffected. So this area, within this area, if you place any crop, the sprinkler can effectively spray water onto it. Just like that, if you place a positive charge, let's say Q, and then if you place a unit positive charge and it experiences a force due to this positive Q, then you can say that the force experienced by this positive test charge, which is unit test charge, is due to the field exerted by this positive Q charge. So to put it in simple perspectives, field just means that electric field in this case simply means that it is the area surrounding that charge where its influence is felt. So how can we represent this field? So if we have a charged particles, we cannot simply draw little circles around it. So we actually have to have a direction. We know that if it is a positive charge, it will be acting in a different way. If it's a negative charge, it will be acting in a different way. So how can we actually represent that? Again, we have to use the help of vectors. So vectors can actually help represent the field of a charged particles. So we can see that the positive charge, let's say this is a positive charge, the field lines will be going out, and the number of field lines will represent the strength of that electric field around that particular particle. And as we move away from that particle, as the distance increases from that point charge, the strength of the electric field will be very weak. So as we move closer to the charged particle, the strength of the electric field will be more. How do we know that? By just observing the field lines. So these are known as field lines. So these are known as field lines, and these are vectors. So this has a particular direction and it has a magnitude. So the field lines will give the strength of the electric field, where it will be very large near the charged particle, and as we move away from it, the concentration of the field lines will decrease, which means that the electric field dissipates over distance. And if this is for a unit positive charge, the unit negative charge will be completely opposite in direction, which means that the unit positive charge will exert the field lines outwards, while the unit negative charge, the field lines will be directed inwards. So that is the only difference. Because the polarity is different, the direction will also be different. So the thing to remember here is that charged particles will have electric field around them. It is just the area under which the influence of that charged particle is felt, or the area under which it can exert a force if another charged particle is placed in that reach. And since now we understood what a field is and what field lines are, we have to calculate what the electric field is. So the electric field E, the electric field is represented by the letter E, which is a vector quantity, is given by the equation K Q divided by R square. So what does this actually mean? It says that the electric field is equal to Q by R square and there is a constant. So if you can read an equation properly, you can actually understand the concept behind that. So what this actually means is that the electric field is directly proportional to the charge of the particle. If we have a small particle, let's say this is a small q, then the electric field will be small. So this is the area under which the electric field is felt, and this will be small. But let's say we have a heavier charge particle, and the area under which its influence will be felt will be much more larger. That is, depending on the magnitude of the charge, the electric field will increase or decrease. So that is understood from this equation. And it is also inversely proportional to the square of the distance. That is, as we move further away from the charge, the intensity of the electric field decreases. How do we know that? Simple. As I said earlier, imagine that these are all the field lines represented from this positive charge. And if we take an area here and an area here, which is same, you can see that the number of field lines penetrating to the region 1 is more compared to the region 2. If, let's say, 2 field lines are barely penetrating it, here there are 3 field lines. So as the distance increases, the field lines or the strength of the electric field decreases. And that is the beauty of equations. If you know an equation and you know how to read it, you can actually construct laws and concepts behind that equation. For this equation, we know that the electric field increases with magnitude and it decreases over a large distance. And this is a vector quantity, and this is the equation to find the electric field of any substance. And since we know this, let's move on to another concept which is known as flux. So what exactly is flux? Flux actually means that how many field lines are penetrating through a given area. So in order to find out the flux, we have to first determine an area through which the field lines are penetrating through. So in this case, the field lines are going in this direction. So if we take an area which resembles a sheet, let's say a rectangular plane is taken here, and here you can see that field lines are penetrating in this direction, and it is normal to the rectangular sheet we have taken. And if we rotate this area, let's say we rotate this like this, and it is parallel to the field lines. And when this is parallel to the field lines and at an angle of 90 degrees, then what happens? Then the field lines are passing like this, parallel to the area we have taken, and the angle between the normal and the field lines will be 90 degrees. In that case, you can clearly see that there is no penetration effect here. The field lines are not penetrating the given area. Instead, they are moving parallel to it. So there is zero penetration, which means that the flux given will be 0. And finally, when it is at an angle. So at first, the normal and the field lines were parallel to each other, which means that the normal and the field lines are at an angle of 0 degrees. And when it was rotated 90 degrees, the field lines are not penetrating through it, so the flux will be 0. And when it is at an angle, let's say it is at 60 degree or 30 degree or something, what if this goes in an angle? So that is when the rule of vector addition again comes into play. So what does that actually mean? It means that imagine that you're being pulled in this direction and you're being pulled in this direction simultaneously. So 2 of your friends are pulling in this direction and this direction simultaneously. But you cannot go in this direction and this direction because the forces are like that. If one force was dominating, then yes, but none of your friends are skinny and they are very strong and they are equally strong. So they are pulling you in both in this direction with a force F and in this direction with a force F. So what will happen? You will move in this direction as a result of the forces applied in the other 2 directions. And just like that, we can resolve this resultant vector into vector components as sine theta and cos theta, which you have studied in PUC first year. So just refreshing the concepts. And since here also this is at an angle, we can conclude that the electric flux will be given as a result of the magnitude of the electric field and the area which we have considered. So what does exactly all this means? This is all a bit messy and you don't clearly understand what this is. So to clearly explain that, let's see one more thing. So imagine that again you have a charged particle. Imagine that you have a charged particle and you've taken a region, and imagine there are field lines coming out of this charged particle. So you have taken this small area here. On the surface, you have taken a small area which is dA. dA just means small area. If it's a large area, you can just take it as A. So this is N, which is the normal to that area. So you have taken this as a small area. Then if you draw a perpendicular like this, and that is known as N cap, which is just the normal. And finally, there will be field lines coming out like. So the field lines will be coming, let's say, in this direction. So how do we define flux? Flux is denoted by the letter phi. This is a Greek letter. And phi is given by, or phi is equal to, the magnitude of the electric field. So how strong this electric field is. So near it will be stronger, here it will be more stronger, here it will be slightly weaker. So depending on the magnitude of that electric field and the area, E dot dA. So depending on the magnitude of that electric field and how much area it is penetrating, or simply how many field lines are passing through that given area. So depending on that, you will get flux. If there is high electric field strength or the magnitude of the electric field is very high, the flux will automatically be very high. And if more number of field lines are passing through that given area, then the flux will automatically be high again. So this is given by E dot dA. And technically you also have to write N caps, which is the normal, but most of the books does not write it. And if the electric field lines are moving at an angle, then you can clearly say that electric field times the area and cos of the angle between them will give the electric flux. So remember that the electric magnitude of the electric field, the area under which the field lines are passing through, and the angle between them if it is placed at an angle. So the electric flux can be found out through this equation. And what this equation clearly means is that phi is equal to E dA cos theta. What it means is that depending on the magnitude of electric field and the area under which the field lines are passing, you will get the electric flux. So what if cos theta is 0 degree, 90 degree, and let's say some other angle in between? So if it is 0 degree, then you will have maximum flux, which is just simply EdA. And I'm just taking for the small area. If you want it for a large area, you can just take it as A. Then it will be EA. If you're considering this whole area, then this is simply EA. If cos theta is 0 and if it is 90 degree, it means that no flux is actually coming through it. So then it means that E into cos 90 will be 0. So E into 0 into A, area cannot be 0. So the field lines are not penetrating any given area. And if more number of field lines are going in than coming out, then that equation can be negative. If more number of field lines are coming in instead of going out, it can be positive, and it can also be 0. So essentially what phi or flux simply gives us is that the amount of field lines in a given area. So there is actually an easy way to imagine electric flux and understand what it really means in a simple way. So imagine that you have a pipe. So this is a pipe. So the important thing about a pipe is that we know it has a particular volume, it has a particular area. So imagine that this is the length, breadth and size of the pipe. So we know that through this particular area, water will be flowing out, right? So this particular area, water will be flowing out. Just like that, if we take a particular area near an electric field, field lines will be coming out. So depending on how much flow is there, how much field lines are penetrating it, the amount of flux is determined. Depending on how much water is coming out, the amount of flow is predicted. Just like that, depending on how much electric field lines are passing through that given area, the flux of that area is calculated. And if the water pressure is more, then more will come out, right? Just like that, if the electric field is stronger, or the magnitude of electric field is higher, or simply more will be the electric flux. And if the area is larger, then more water will come out, right? If this is the area, more water will come out. Just like that, if the area is higher, more field lines will be penetrating it. And depending on the angle, the flow rate will also change. Depending on the angle, the rate of flux will also change. That is simply how you can correlate the flow of electric field lines through a given area. So that is what exactly is given here. So electric field lines are penetrating a given amount of area. And we know now what a normal is. It is just a perpendicular drawn to the area we have taken for reference. So we can see here that normal is in this direction and the electric field lines are also in this direction, which means that they are just parallel to each other. The angle between them is 0 degrees. Now, when we introduce the equation, which is phi is equal to E A cos theta, which means that E is the electric field and A is the area of this. In the last part, we have only taken out a small area dA, but here we have taken out the entire area, which is A, and cos of the angle between them, which is cos 0 degrees, cos 0 degrees. So, which is just E times A, because cos 0 is 1. And just like that, here it is cos 90 degrees. E A cos 90. Why is it 90? Because angle between the normal and the electric field is 90 degrees. That is why EA cos 90. And cos 90 is simply 0. So this is 0, which means that there is no flux present in that particular area. As you can see that when the area taken is parallel to the field lines, it means that the field lines are flowing in the direction we have taken. So it simply means that there is no penetration of field lines in this particular area. And when we come here, as you can see in the earlier case, the normal and the field lines are at an angle, and we can use this equation, which is E cos theta into A, or EA cos theta, to calculate the flux of that particular region. And again, moving on to the next topic, we'll be discussing about electric dipoles. So what exactly is an electric dipole? So we know that there are negative charges and there are positive charges, because we have studied polarity and we know what Benjamin Franklin told us. And if there is a pair of positive and negative charges, that is, there is a positive charge and a negative charge separated by a distance of 2a, that is, up to this point it is A, up to this point this is also A. So two charges which is opposite in polarity but equal in magnitude. So if this is Q, this also should be Q, but one should be positive and the other should be negative. That should be the only difference between these two charges. The magnitude of that charges should be same. So if there are two charges equal in magnitude but opposite in polarity, separated by a distance 2a, then this is known as an electric dipole. Di meaning two and pole meaning, you know what polarity is, which just means is it positive or negative. So an electric dipole is nothing but a pair of equal and opposite charges separated by a distance of 2a. The direction of the dipole is minus q to q, which just means that the direction of the dipole, because dipole is a vector quantity, we can say that the direction of the dipole, the direction will be from minus to positive. So this will be the direction of the dipole. And now we can represent it in an equation form again. So we can represent it as P, that is the electric dipole. P is equal to 2 into Q into A. So that simply means that 2Q A. So this is the equation for an electric dipole. So in the coming classes, we'll learn about how to calculate the electric field due to a dipole, because these two are again charges. So these two charge particles will have an electric field around them, and since there is an electric field around them, there will be a force experienced by any particle placed in that region. So we will calculate the force experienced by that particle and the electric field at that particular point due to these two charges in the coming classes. What if we place it here? What if we place it, let's say, here? Is there any difference between them? Is there any similarity between them? Or is it completely different? Is it relevant? Everything will be discussed in the coming classes. So in this class, we have learned about what electric field is, what electric field strength is, and how charges interact to each other. And we understood what Coulomb's law actually means. And we also studied about electric flux, and we introduced what electric dipole actually means. So one thing to actually remember is that if there is an electric field, let's say this is a positive particle and this is a negative particle, the field lines will be directed outwards for a positive charge and inwards for a negative charge. And the one thing you should know is that field lines can bend and curve, but it does not form closed loops. It does not form closed loops. And if there is a negative charge nearby, it can travel from positive and end in negative. But it cannot travel from negative and end in positive. These are some things you have to remember. They cannot form closed loop around each other, and two field lines cannot cross over each other. Why two field lines cannot cross over each other is because each vector field line represents a particular direction. So when two vector field lines cross each other, there will be a question of where is it going. If we take the center point here, we cannot precisely say which direction it is going in. So since there is an ambiguity in the direction, that is why two vector field lines or two electrical field lines can never cross each other. So those are some things you actually need to remember. And then finally, we studied about what electric field lines are, what electric flux is, and the physical significance of it. And finally, we also studied about what electric dipoles are. And in the next class, we will study how electric dipole actually interacts with particles placed in different points. That is all, and I'll see you all in the next class with more electricity. Thank you.